So we're now familiar with the mechanics of time-inhomogeneous Poisson processes, and a natural next step in expanding our arsenal of statistical tools for the model class is building a simulation scheme for such processes. So for today's lecture, it's going to be a bit of a mix between theory and code, where we'll first cover the calculus of simulating time-inhomogeneous Poisson processes, and then we'll dive into an R session so that I can show you how all of it works. Now, for purposes of preparation for the R session, I suggest you just revisit the lecture on simulating homogeneous Poisson processes. Indeed, you'll see that there's very little modification actually required of that algorithm to simulate time-inhomogeneous Poisson processes. But in any case, you do need to understand it. So let's jump in. So the starting point of the analysis, as usual, is by way of a theorem. And it goes as follows. Suppose events occur according to a homogeneous Poisson process with rate parameter lambda. Suppose further that independently of the history of the homogeneous Poisson process, an event that occurs at time t is counted with some probability, let's call it pt. Then the process of counted events constitutes a time-inhomogeneous Poisson process with intensity function lambda t, which is just equal to lambda times pt. So where lambda is from the homogeneous part and pt is the selection mechanism or counting mechanism. Okay, so essentially what this theorem states is that, well, we sample from a time homogeneous Poisson process in such a way as to generate a time inhomogeneous Poisson process. Okay, and the way we do that sampling is dictated by the probability or probability function pt. Okay, excellent. So for the proof of this theorem, what we need to do is we need to show that the sampled process, i.e. those events which are counted, is a time-inhomogeneous Poisson process with the appropriate intensity function. Okay, so how did we define what a Poisson process was? Okay, well, we need to look at the Poisson Postulates. So we need to show that for the counted or sampled process, the Poisson Postulates are satisfied in the time-inhomogeneous case. Okay, now as it happens, postulates 1, 2, and 4 are satisfied for the sample process, since they will hold for the homogeneous Poisson process. Okay, so let's clarify what that means. What was postulate 1? Well, we're counting from 0, right? So if we're selecting events from a homogeneous Poisson process with a certain probability, we're still counting from 0. Okay, our count might differ by the end because we select with a certain probability, but it will nevertheless be satisfied. What was postulate 2? Well, under the time-inhomogeneous case, well, we had independence of the increments. Now, the homogeneous part is, it will have independence of the increments, but it also will have stationarity. Here we're selecting with a probability which is a function of time, so we lose the stationarity, but we still have the independence because, well, we're selecting from a homogeneous Poisson process. Okay, now how about postulate 4? Well, postulate 4 had to do with observing 2 or more events in a short interval of time, say h. Okay, well, that will hold for the homogeneous part. Okay, so if we're only counting as many or fewer events than we observe in the homogeneous part, well, then that has to hold for the sampled process as well. Okay, so that takes care of postulates 1, 2, and 4. Now, postulate 3 is seen to be satisfied by noting the effect of the sample mechanism, right, on the count. So what did postulate 3, what was it concerned with? Well, it was concerned with the probability of observing one event in an interval of length h. Okay, so let's consider that probability. So the probability of observing a count in an interval running from, say, t to t plus h being 1. Okay, well, because we're counting with a certain probability, we're looking at one event here. Number of ways in which that could have occurred. One way is one event happens in that interval of length h and we count it, or 2 or more events occur in that interval and we count one of them. Okay. Now, from our homogeneous part, we have a probability of observing one event. From our sample mechanism, we have the probability of counting that event. We also have that again for the probability of having 2 or more events. Well, that's inherited from the homogeneous part. And then we still have our counting mechanism. Okay, so we can actually write those probabilities in terms of their constituent parts. So the first part, so the probability of having one event in an interval of length h and it being counted, is just lambda h time or plus terms which are little o h. Okay, so that's the probability of observing one event in that interval from the homogeneous part, and then we count it with probability pt independently of the trajectory of that process, so we just multiply it by pt. Okay, so that's lambda h plus terms which are little oh, all of it times pt. And then again, from the homogeneous part, what's the probability of observing two or more events? Well, that's just going to be little oh. And what is the probability of counting that event? Well, pt. There you go. Okay, and then we simplify the calculus. Remember, the little oh tends to gobble up terms, and then we end up with the appropriate intensity function, which we find to be lambda times pt times h, okay, which is just lambda t as stated in our theorem. Okay, plus terms which are little oh. Okay, and that establishes the theorem. Cool. Now, using this theorem, we can put together a simulation procedure which builds on our simulation scheme for homogeneous Poisson processes. So here goes. It's called a thinning algorithm. I'll explain why it's called a thinning algorithm in a second. Cool. So we'll consider the case of simulating a time-inhomogeneous Poisson process with intensity lambda t, so intensity function, and this time in fixed window mode. So we consider a window running from 0 to b. Okay, now the scheme will be exactly the same for fixed count mode. It's just that fixed window mode is more applicable for the types of questions we like to ask. So we'll just cover that here. Okay. The algorithm goes as follows. So first, select a constant rate parameter. This time I will refer to it as lambda plus. Okay, so just to make clear that it has to be greater than or equal to the intensity function lambda t for all t in the interval running from 0 to b. Okay, and then we'll set the selection probability or sample probability pt to be lambda t, so the intensity function divided by this lambda plus. Okay, now you can already see where this is going, right? We need a counting mechanism or sample mechanism, and we need a homogeneous Poisson process. Okay, so we're going to sample from a homogeneous Poisson process with rate parameter lambda plus, and then we're going to select that or events from that process with probability pt, which we'll just set to the function, the intensity function divided by whatever that lambda plus is. Okay, so now you can see why we need that lambda plus must be greater than or equal to the intensity function. It's because we need that function to be a probability. Okay, now again, I just use lambda plus here to emphasize that it has to be greater than or equal to that function. Cool. So here goes the steps of our algorithm. Step 1, and this is going to be the homogeneous part. Draw random uniform 0, 1 random variables, UK for k running from 1, 2, 3 all the way up to n star. Okay, then set the inter-arrival times tk as equal to -1 divided by lambda plus log UK, and then set the arrival times sk as equal to the sum for all I running from 1 to k over all ti for k now going from 1, 2, 3 all the way up to n star. And again, what is n star? N star is given by the maximum n such that the sum of the inter-arrival times is less than or equal to the window width. Okay, so remember, we are simulating in fixed window mode. How do we do that? Well, we draw inter-arrival times, we add them up until we exceed that window, we step one back, and then we say, well, that's our n star. That's how many events have occurred in that interval. Cool. So up to where we are now, we are still just simulating a homogeneous Poisson process. Now comes the sample mechanism, which will generate the time-inhomogeneous process. Okay, so step 2, generate independent uniform 0, 1 random variables. Okay, so these are new random variables, hence you'll see wj, such that j runs from 1, 2, 3 all the way up to n star, and then compute the following indicator. Okay, set ij to 1 if this wj is less than or equal to lambda evaluated at the arrival time sj divided by lambda plus. Otherwise set it equal to 0. Okay, and do this for all j running from 1, 2, 3 all the way up to n star. Okay, so what is this step doing? It is selecting with probability psj. essentially. Cool. Step 3, let cal j denote a set of indices j where j is such that the indicator ij is equal to 1, right? Then the count trajectory will go 1, 2, all the way up to however many sets or however many elements are in that set. So just sum over all of the indicators that are 1 to get that number. And then the arrival times, okay, will be those arrival times from the homogeneous part, okay, for which j is in that set, cal j, i.e. Those j for which the indicator is 1. Okay, so you can see what these steps have now done. They've essentially sampled or generated a homogeneous Poisson process, and then from the generated arrival times, selected from them using a certain probability, and the resulting arrival times will be then that of a time-inhomogeneous Poisson process with intensity function lambda t. And that's why this is called the thinning algorithm, right? Because you start with a homogeneous Poisson process, you generate some arrival times, and then you thin out those inter-arrival times using some sample mechanism, which then generates the time-inhomogeneous Poisson process. Okay, so that's that for the theory. Let's jump into the code. Okay, cool. So let's kick off the code. As usual, I've got a template file. We've got one overarching goal and then a bunch of subtasks. And the goal is to simulate a time-inhomogeneous Poisson process and compare the mean count from a number of simulation trajectories to a corresponding theoretical value. Okay, so we're just going to simulate something. We're going to see if it compares well to the theoretical value. We've got two subtasks. Task 1 is just to simulate a realization of the Poisson process over a particular window, and we're going to plot a trajectory. Task 2, we're actually going to do the multiple simulations, so simulate 10,000 trajectories. We're going to calculate the mean observed count and compare that to the mean value function. Okay, and I give you a bunch of things. I've already set C to 4, 3, 2, 1. That's just so we always get the same results. What else have I given you? Given you window width. Oh, I've given you the intensity function, so the lambda, and then I've also given you the mean value function. So we can compare that to the theoretical value. Okay, cool. So let's kick off with task 1. Task 1 says simulate the realization of a Poisson process with intensity function lambda t equals 20 plus 10 sine 0.5 pi t under a fixed window mode on 0 to b for b equals 10, and then plot the process trajectory. Okay, so I give you b equals 10. We set that parameter. I give you the intensity function already set up. Got 3 interim steps. Simulate the homogeneous path, sample with using the appropriate probability. So remember, how does the algorithm work? We sample from a homogeneous Poisson process. Okay, and then we're just going to plot the trajectory. Okay, so let's do the homogeneous part. So that's nice and easy. Actually, before we start with the homogeneous part, if we want to simulate the homogeneous part, we need to pick an appropriate value for its rate parameter. And how do we need to pick that? Well, we need to pick it so that it's such that it's always greater than this intensity function that I've given you. Okay, so let's pick a value. Okay, how we're going to do that is let's quickly plot. So we're going to create a sequence TT running from 0 to b in steps of 0.1. And then we're going to plot the intensity function. So lambda as a function of tt type equals L, so a line plot. Okay, so please create a line plot, and then we're going to read off from our plot what an appropriate value is. Okay, yeah, I guess we could have just looked at the function. We could have guessed that it might have been 30 would be a good value. Why? Because, well, 30 will always be greater than or equal to this function, right? So let's go AB line. And let's go make a horizontal line at 30. Yes, okay, cool. So we see that that's the case. Okay, cool. I'm just going to suppress these for now. So let's set a new parameter. Let's call it lambda plus equals 30. Okay, we're going to set our rate parameter for our homogeneous part of the process to that. and then we're going to simulate from that. Okay, we need to set B. B is 10. Okay, so first thing we're going to do is we're going to make draws for our inter-arrival times. Okay, how many? Well, we don't know because it's fixed window mode, so let's just pick a large number for now. Okay, so we're going to round 3 times B, which is the interval width, times lambda plus, right? Okay, why is that? So the expected count is B times lambda plus. We're just going to 3 times that, so you're going to simulate. We're definitely going to overshoot the window and then just throw away whatever's there. Okay, it's not perfect, but it's a nice and convenient way of doing things. Okay, so then first thing we need to do is we need to make random uniform draws. So random uniform, how many M, where M was the 3 times whatever the expected count was. 0, 1. Okay. Then we're going to set the inter-arrival times. So let's put that in a vector called T, and that's going to be minus 1 divided by lambda plus, okay, times log whatever U is. Okay, so from the inter-arrival times, we need to set the arrival times. Okay, so that's just going to be the cumulative sum of what? The inter-arrival times. Okay, so vector S is now our vector of arrival times for a homogeneous Poisson process, and well, under fixed count for M. Okay, but we want to simulate over fixed window mode. Okay, so we need to trim those if there's more than what we need for the window. Okay, so we're going to take whatever that vector is, and we're going to say from the vector X, just retain those for which the arrival times are less than B, okay, where B is the endpoint of that window. Okay, so this is what it's doing. We're taking the vector S, we're indexing it such that this statement is true, so S less than B. Okay, so whenever this is true, it will retain those events, and then it'll chuck the rest. Okay, so this new vector S, we've just reassigned it. That's going to be our arrival times for our homogeneous Poisson process simulated over a window running from 0 to B with rate parameter lambda plus equals 30. Okay, so what we need to take from this is n star. We don't know how much that will be because we're in fixed window mode, so that's just going to be the length of S. Okay, cool. So where to from there? Okay, so we've just simulated the arrival times for the homogeneous part of the algorithm. Next, what we need to do is sample using the appropriate probability from that homogeneous Poisson process to give us the non-homogeneous Poisson process. Okay, so for that, what we need to do is we need to simulate a new set of random uniform deviates. Okay, how many? N star. Why? Because we need 1 for each arrival time that was generated in the homogeneous part of the process, because we're going to select, for at least for each one of those, we're going to decide whether we select that arrival time or not according to a particular probability. Okay, and this is where this W is going to feature. So we generate that vector. What's next? Oh, we created a vector of indices. So this is that, or indicator variables. Okay, so what we're going to do is we're going to check whether this W is less than or equal to, what was the statement? Well, it needed to be less than or equal to the appropriate probability evaluated at the particular arrival times, right? So remember, we've got N star W's here. We've got N star arrival times from our homogeneous process. So for each one of those now, we're going to compare the random uniform deviate to a particular probability evaluated at that arrival time. Okay, and that probability is just going to be the intensity function, so lambda evaluated at the arrival times divided by lambda plus. Okay, cool, and that gives a logical statement. So let's quickly run this, and then I'll just show you what this vector looks like. Okay, so what does end look like? So n is going to be a number of true and false statements. Okay, so we wanted to have an indicator variable, so we wanted it to be ones and zeros. So what we can do in R, we can actually take these Boolean values and we can multiply it by 1, and then it'll know to turn it into, I guess, integers. Okay, so let's do that instead. So I've multiplied there by 1, and then we get our indicator variable. Okay, so you see there. So it'll be 1 for where that statement is true and 0 elsewhere. Okay, and we do that for all of the arrival times. Okay, and how many were there? There were n star, so 317. Okay, brilliant. So those are indicator variables. Next we need to do is, okay, we want to maybe plot the trajectory. So let's create a trajectory. So the count sequence, that's just going to be nt, is going to be running from 1, well, I guess from 0. Yeah, okay. Let's go 1 to whatever the sum of the indicators are. Okay. Yeah, because that's how many events we've selected from the homogeneous part. Okay, so now nt here is now the non-homogeneous processes count. Okay, and its first element's going to correspond to the first arrival which we've selected. Okay, and which are the arrival times that we have for this process? Well, we're going to reassign S again. Okay, so S is now going to be well, let's do this. Let's create, otherwise it's going to create confusion about that set, that cal j. Okay, so let's create that set cal j. What does this set cal j look like? Well, it's all the indices for which the indicator variable is 1, right? Okay, so what does cal j look like? So let's just run everything again. Okay, so cal here says, well, for which of the elements was the index 1 or the indicator variable 1? It's going to be 1, 4, 5, 6, 7, whatever. And these are the ones that you select, right, from the simulated arrival times. Okay, so when we reassign S, what we now are going to do is we're going to take that S and we're going to say, well, which of those are 1? Okay, so we can just say, well, J already counts for that. That's the index set J. Okay, so reassign S, and those will be the arrival times for our non-homogeneous Poisson process. Okay, cool. So brilliant. Next up, plot the trajectory. Okay, how are we going to do that? Let's go. All right, let's just plot the nt as a function of what? As a function of S. And I'm just going to go type S here. Okay, so let's rerun everything. Cool. Okay, so you can almost see the sinusoidal pattern in the trajectory of the process there. Okay, brilliant. And we see that we had about just over 200 events. Okay, cool. But we also said last time, I believe, that we're not quite satisfied with the way that we plot that trajectory, because it doesn't count for starting from 0, whatever. So technically the correct way to do this would be, let's prepend the count sequence with 0, and then just again with whatever the max of nt is. Okay, and then let's prepend the arrival times with 0, and then whatever the end of the window period is. Okay, cool. And let's just plot that. Okay, so then there we have our technically correct plot. Okay, cool. So that's that for task 1. We've simulated the process once. Now we're going to simulate it a number of times. So simulate 10,000 trajectories and calculate the number of events at each iteration. Okay, so from our one single trajectory, we want to check, okay, from our single trajectory of a non-homogeneous Poisson process, we want to check how many events occurred in the appropriate window, store that, calculate the mean of all of those trajectories, and then compare that to the theoretical mean, which we can calculate via the mean value function. Cool. So how are we going to do that? Well, I suggest what we do is we set up a function. Okay, so I'm just going to call it sum for now, rather unimaginatively. And what we're going to do is we're just going to copy all our code. Well, let's just do that. Let's copy this code. What else do we need? Let's take that as well. And let's take this bit. Okay, so every time we run this function, it's going to rerun a simulation of this process, and we just want it to return a list. List of objects. Well, what do we want? We want the arrival times, so return the vector s, so s equals s, so that has the appropriate name. Also give me back the trajectory, nt equals nt. Okay, for now that's going to be good enough. Then what we want to do, we want to simulate that 10,000 times. We want to store the maximum count that we observe. So, okay, so let's create some storage. So I'm just going to say store equals c. So I'm going to create an empty vector. R will know what to do with that. This is not a particularly efficient way of doing things, but in any case, we'll do it this way. Small scale simulation. Okay, so store equals c, creates an empty vector, and then we're going to loop. We're going to run from I in 1 to 10,000. Okay, we've got our little loop. What are we going to do? Well, we're going to restore the result from our simulation. And what is the result? Okay, well, we need to, let's call the function sum. Okay, what is sum going to do? Sum is going to return a list with all of these elements. The thing that we're interested in here is the count. So res, return the count trajectory. And in particular, we are interested in the total count observed over that window. Remember, sum is going to simulate over that window of time. So we just want the last element. So let's just have it store at each iteration the max of the count trajectory. Okay, and then what we want to do is we want to calculate the mean over all of those simulations of the observed max counts for each simulation. Okay, so I'm just going to rerun everything from that. So we've wrapped everything in a function. Okay, let's hope it works. Okay, and we get a mean of 213.09. Okay, cool. That's probably with an error. Okay, so that gives us an idea of the expected count for a process with intensity function 20 plus 10 sine 0.5 pi t over the window running from 0 to b equals 10. Cool. Now, hopefully our simulation algorithm was accurate, so maybe we can compare it to a theoretical value. What was the theoretical value? Well, we can evaluate that in terms of the mean value function. I've given you the mean value function here, so you can just evaluate that function at the endpoints. What are the endpoints? B and 0, subtract them, and that'll give you an idea of the true expected count in that interval. And let's compare that. And indeed, we see it's 212.73. Okay, so we got quite close. Okay, cool. So I guess that's that for now. Maybe if you want to, you can play around with this algorithm, maybe dream up some other expressions for the intensity function, and yeah, see how it works. Cool, so I hope you found that interesting. As simulation schemes go, we could make an entire series on the nuances of simulation. And now that we're getting comfortable with the simulation schemes for Poisson processes, we could actually start interrogating the quality of these algorithms. Indeed, there are at least two issues with the present algorithm. One's got to do with how we coded the algorithm. The other's got to do with computational efficiency. But that's a topic for a separate video. So for now, I'll just leave some problems on screen for you to check out, and then I'll see you in the next one.